everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to understand the reactions of benzene with oxygen and air, bromine in the presence of a catalyst, a mixture of concentrated nitric and sulfuric acids, and halogenate-alkanes and acyl chlorides with aluminium chloride as a catalyst. Our last learning objective will be to understand the mechanism of the electrophilic substitution reactions of benzene. So this is halogenation, nitration, and Friedel-Crafts reactions, including the generation of the electrophile. Now we're going to talk about electrophilic substitution. So the delocalized electrons of arenes, so of compounds with the benzene group, have a high electron density and will therefore attract electrophiles. So we get this reaction of electrophilic substitution. Remember that electrophiles are species with a vacancy for a pair of electrons to form a covalent bond. So the general mechanism that we have is that a bond forms between one of the carbon atoms of this arene and the electrophile. And the carbon must use electrons from the delocalized system of the arene, and so this delocalized system is temporarily destroyed. In order to get the stability back, the carbon loses a H+ ion, and the overall result is the substitution of the electrophile. So we substitute a hydrogen for the electrophile. So key things to note are that the delocalized system gets temporarily destroyed, and the carbon loses a H+ ion, and that's what's substituted out. So if we're going to look at a general mechanism of this, for example, I'm going to use benzene. So this is the structure of benzene, and then I'm going to add an electrophile. So electrophiles will normally be positively charged because they've got that vacancy for a pair of electrons. And then what happens is that because we've got a high electron density in the middle of this benzene due to the delocalization of electrons, they are attracted to this electrophile. And so a bond forms between one of the carbons of benzene and the electrophile. So what we get is, again, we draw the hexagon, but this time we're going to have a temporarily destroyed benzene. So the delocalized system is temporarily destroyed. And so on this carbon, we're going to have a hydrogen, and I'm going to attach the electrophile also onto this carbon. And one thing to note is with the first diagram of benzene that I've drawn, obviously we assume that each carbon has one hydrogen attached. So now we're just honing in on one of these carbons that I've attached the electrophile to. And one rule that we need to know is that when we draw a dotted line here, how we've drawn this temporarily destroyed delocalized system, the two ends here and here can't exceed this green line. And so, for example, we could have a hexagon that looked like this. And if you wanted to add the electrophile, say, onto this carbon here, so you draw the hydrogen, and if you wanted to add the electrophile here, we then would draw a green line here, and the C that you're kind of drawing can't exceed this green line. So what we would draw would be something like this, and we'd have the positive. So looking back at our original equation, what happens next is that in order for us to get the stability of the delocalized system back, so to fix the delocalized system, this carbon, which has now attached itself to an electrophile, needs to lose a H+, so it needs to lose the hydrogen that it's attached to. And so what happens is that the electrons from this covalent bond move to this positive charge, and then we get benzene, and then we get benzene, but now with an electrophile attached, and the H+ comes out. Now we're going to look at nitration. So this is a reaction when one of the hydrogens in the benzene ring is substituted by an NO2 group, so nitrogen dioxide. And so we call it an electrophilic substitution reaction. And that's because the attacking group we have is the NO2, and the NO2 acts as an electrophile, and we're substituting one of the hydrogens, so it's a substitution reaction. So the reagents we need are concentrated nitric acid and concentrated sulfuric acid, and the sulfuric acid acts as a catalyst. The condition which we need is 55 degrees Celsius, and this is really important because this prevents further substitution. The electrophile that we're using is this NO2 plus ion, which is also called the nitronium ion. So as an example, we're going to look at the mechanism of the nitration of benzene. So the thing to remember about nitration is that first we need to actually produce the electrophile from concentrated nitric acid and sulfuric acid. So I'm first going to look at the equations for producing the electrophile. This will always be the first step of your mechanism. And so what happens is we have some nitric acid and also some sulfuric acid, and they react together to form H2NO3 plus and HSO4 minus. So why this happens is that the sulfuric acid is a stronger Bronsted-Lowry acid and so that means that it donates a proton or H plus to the HNO3. So what happens is that H2SO4 is acting as the acid and HNO3 is acting as a Bronsted-Lowry base, so it's accepting a proton. And then what happens in the second step, so this is the first step we have, and then in the second step we have that this H2NO3 plus ion will go on to form this NO2 plus that we're after. This is the electrophile that we're going to use for the substitution reaction, and water. So this is the second step. And what happens here is that H2NO3 plus loses water. And so now we can write an overall equation for the production of the electrophile. So overall, we have that nitric acid added with sulfuric acid. So remember, they both have to be concentrated. They produce HSO4 minus and NO2 plus and water. So again, this NO2 plus is what we call the nitronium ion. And this is what's going to act as the electrophile in the reaction. So now we get on to the actual substitution. So what we have, this is step 2, the electrophilic substitution. So we first draw out a benzene. So we'll have benzene here. And then what we have is the electrophile, which is the NO2 plus. So we have NO2, and I'm going to draw a plus onto the nitrogen. And now if you remember, what happens is that because we have these delocalized electrons in the benzene, and this is an area of high electron density, and so it attracts the electrophile. And so delocalized electrons move towards this positive charge of the electrophile of the nitrogen on this nitronium ion. And so now what happens is that we've temporarily broken the delocalized structure. So we still have the outside hexagon of carbon atoms, but now we're going to have this broken delocalized structure inside. So I'm now going to hone in onto this carbon, which I'm attaching this electrophile to, and I've got the hydrogen. And remember that in order for us to fix the delocalized structure, we need to lose a H+. Well, the carbon needs to lose a H+. And so the electrons from this bond move towards the positive charge. And so what we form is we have benzene, but now attached to an NO2. And so this is nitrobenzene. And we also form the H+. And again, this is an electrophilic substitution reaction. So overall, as a balanced equation, including the production of the electrophile and this substitution, what we get is that we have a benzene added with some nitric acid, and we're going to use a sulfuric acid catalyst, concentrated, and the nitric acid is also concentrated, and we also use a temperature of 55 degrees Celsius to prevent further substitution. And what we produce is this nitrobenzene and also water. So again, we need to remember that this is an electrophilic substitution reaction, as the attacking group is an electrophile, it's the NO2, and we're substituting, this NO2 is substituting a hydrogen, and so it's a substitution reaction. And nitration is quite important because it's the first step in the production of explosives. And it's also important in the first step in making amines, which are used to make industrial dyes. So now we're going to look at Friedel-Crafts Alkylation. So when benzene is reacted with haloalkanes with aluminium chloride as a catalyst, we can produce alkyl benzenes, which are just benzenes attached to alkyl groups. So for example, we could have benzene, which was attached to, let's say, a methyl group. So this is methyl benzene, and this is an example of an alkyl benzene. And these are electrophilic substitution reactions, because the attacking group is an electrophile, and we're substituting it in for a hydrogen. So the example we're going to look at is the reaction of benzene with chloroethane. The reagents we're going to use are chloroethane, and also in the presence of anhydrous aluminium chloride catalyst. So anhydrous just means doesn't contain water. The conditions we use are that we have it heated and under reflux. So that's when the condenser is on top of the heating flask. And the electrophile we're using is the CH3CH2 plus ion. So the first step to this mechanism is always forming the electrophile. And so what we do is we add together the chloroethane with the aluminium chloride, the catalyst, to produce the electrophile. So we have chloroethane, that's CH3CH2Cl, and we react it with the catalyst AlCl3, and then we can form CH3CH2, and we have a positive charge on this carbon, and also AlCl4-. And then what happens is that we can then use this electrophile to substitute in to the benzene. And we've got that area of high electron density in the benzene. So what we have is benzene, and then we have the electrophile, so the CH3CH2 plus. And because of this area of high electron density in benzene, that means that they're really attracted, the delocalized electrons are really attracted to this positive charge. And so they move towards this positive charge on the carbon. And then what we form is an intermediate, so a carbocation. And we get the outside hexagonal ring. But now we have the delocalized system temporarily destroyed. So we put a positive charge here, and we're going to attach it onto this carbon. So this carbon originally has a hydrogen, and now we're going to attach also a ethyl group. And then now what happens is that because this delocalized system is now unstable, so the actual benzene is unstable, we need to remove a H+. So electrons from this covalent bond then move towards the positive charge. And so now we can form our alkyl benzene. So we have benzene, and it's now attached to this ethyl group. And then we also have the H+, which we have substituted out. So we have formed ethyl benzene. And so we have to remember that this is an electrophilic substitution reaction because the attacking group is this electrophile, this CH3CH2 plus ion, and we're substituting it in for the hydrogen. So the third and final step is the regeneration of the catalyst. So what we do is we take the AlCl4- that we formed in step 1. So we have AlCl4- and we react this with the H+ formed in step 2. So then we can form our catalyst and also another product. So we get AlCl3 and HCl. So this is our catalyst that's been regenerated. So overall, the equation that we have is we have CH3CH2 plus added with AlCl4- and also a benzene, and this forms our ethyl benzene. And also our catalyst and HCl. Now we're going to look at Friedel-Crafts Acylation. So this reaction was discovered by Charles Friedel and James Crafts. And this type of acylation is just like any other acylation reaction. And what it does is introduce an acyl group into another molecule. So again, the acyl group is this RC double bond O group. And when we react arenes with acyl chlorides with an aluminium chloride catalyst present, we form aromatic ketones via an electrophilic substitution reaction. And because we're using aluminium chloride as a catalyst, that means that we regenerate it at the end, because we know that catalysts don't get used up in the process, and so we always have to regenerate it. So the reagent we're using is an acyl chloride with aluminium chloride as a catalyst, and the conditions is that we have to have no water, and this is because we need this to prevent the reaction of the aluminium chloride. And the electrophile we're using is RCO+. So it'll be RC double bond O and then a plus. So this is our electrophile. So we're just going to look at a general mechanism. So I'm just going to use a general acyl chloride. So the first step is generating the electrophile. And what we do is we react the catalyst, AlCl3, with our acyl chloride. So I'm going to write it as RC double bond O Cl. And so what this forms is the electrophile we want. So this RC double bond O with the positive charge on the carbon. And it also forms AlCl4-. Now, one thing to know about this AlCl4- is that it's actually a tetrahedral shape. So when we look at it, we have aluminium in the middle, and then we have the original 3 chlorines. So we have a chlorine here, and let's say we have a chlorine here, and also a chlorine here. But now we've got another chlorine which is bonded to this aluminium, but it didn't have any electrons left, and so this is actually a dative covalent bond. So both of the electrons come from the chlorine. And so here we have a negative ion, and this is tetrahedral, because this dative covalent bond classes as a bonding pair. So we have 4 bonding pairs which all repel each other by the same amount, and so the bond angle is also 109.5 degrees. So after this first step, we then need to actually do the substitution. So the second step is electrophilic substitution. So what we have is, first, let's start off with benzene. So we have benzene, and then we have the incoming electrophile. So this RC double bond O with a positive charge. And because we have this high electron density in the benzene, again, because of the delocalized electrons, they are attracted to this positive charge. And so this is how the electrophile attacks the benzene. And so then what we form is an intermediate. So we have the outside hexagon, and now on this carbon, we've formed a bond with this acyl group. And now the delocalized system has also been temporarily destroyed. And we know that this is unstable, and so we need to lose this H plus to make it stable again. So they move towards the H plus, the electrons in that covalent bond, and now we can form our product. So we have benzene, which is now bonded to this acyl group, and then we have the H plus. And so the product we formed is actually 1 phenyl, and then we'll have the name which depends on R, because we formed aromatic ketone. So for example, if R was CH3, then we would have 1 phenyl ethanone, because then there'd be 2 carbons. And so now the last step is regenerating the catalyst. And we always have to remember to do this step at the end. Also, this can come up quite a lot in exam questions, asking you why aluminium chloride is a catalyst, or prove that aluminium chloride is a catalyst. And all you need to do is generate the electrophile from the catalyst, and then regenerate it at the end. So what we have is that the product that we formed when we were forming the electrophile, this AlCl4-, reacts with the product of the electrophilic substitution, the H+, and they react together to form AlCl3 and HCl. So this here is the catalyst that we are needing to regenerate. So now we're going to look at the halogenation of benzene. So we can react a halogen with benzene if a halogen carrier is present. So we have to have this halogen carrier. And common halogen carriers include aluminium chloride, iron chloride, aluminium bromide, and iron bromide. The halogen carriers are generated in situ, and what we mean by this is that it's generated in the reaction vessel from the metal and the halogen. So the example we're going to look at is the bromination of benzene using iron bromide. So at room temperature and pressure, and in the presence of this halogen carrier, in this example using iron bromide, benzene reacts with bromine in an electrophilic substitution reaction. So what we're doing is we're substituting a hydrogen, so H plus comes out with bromine. So the mechanism actually comes in 3 steps. So step 1 happens because benzene is too stable to react with a non-polar bromine molecule. Because when we think of bromine, we have Br2. But because there's no electronegativity difference between 2 bromine atoms, we don't get a polar bond. And so this isn't a polar molecule. And so we don't have a partially positive charge and a partially negative charge on one of the atoms. So we can't actually do the electrophilic substitution. So what we need to do is actually produce a Br plus ion to react with the benzene instead, because the delocalized section of the benzene inside is attracted to a positive ion. So that's why we need Br plus. And this bromonium ion is generated when the halogen carrier reacts with bromine. So this is our step 1, creating this electrophile. So we have bromine reacting with iron bromide, and this will form FeBr4- and also Br plus. So we break the covalent bond between the 2 bromine atoms, and then one of the bromine atoms goes to the FeBr3. So it forms a bond of the FeBr3, and so that becomes a negative ion. And then we get this Br plus, and this is our electrophile. And we know that electrophiles are usually positively charged because electrophiles have to have a vacancy for a pair of electrons to be donated to it to form a covalent bond with something else. And so step 2 is where we actually substitute in the electrophile. So the bromonium ion accepts a pair of electrons from the benzene ring to form a dative covalent bond in an electrophilic substitution reaction. So what we have benzene, and then we have the electrophile, which is this Br plus. And because of the high electron density, because of the delocalized section of the benzene, these electrons are attracted to this positive charge. And so they move towards this Br plus, this electrophile. And now we form an intermediate. So this is exactly like all the other electrophilic substitution reactions that we've seen, all their mechanisms. And so what we have is we have this carbon where it's originally attached to one hydrogen, but now it's also formed a dative covalent bond with this Br plus. And now we know that this delocalized system actually gets temporarily destroyed. So we denote this by a C and then having a positive charge. And so the rule is that when we draw a straight line from between the 2 carbons which are next to the carbon which we've bonded the bromine to, the ends of this delocalized system can't exceed this green line. And so this intermediate is actually very unstable, and so we need to fix this delocalized system. So what happens is that this H plus gets removed. So electrons from this covalent bond move towards this positive charge, and this intermediate breaks down. So then we get benzene, but now attached to this bromine, and we get a H plus, which has been substituted out. And so our product is bromobenzene. Again, we don't need a number because there's only one substituent, so it doesn't matter where we place it if someone told us the name bromobenzene. So now we need to remember that it's an electrophilic substitution reaction. And why is because the attacking group is this Br plus, which is an electrophile, and we are substituting the hydrogen for this bromine, and so it's a substitution reaction. For step 3, we then have to remember that the halogen carrier is actually a catalyst, and so it doesn't get used up in the reaction, and so we have to regenerate it at the end. So how we do that is we take the H plus we've just formed during the substitution reaction. And so how we do that is take the H plus that we formed from the substitution reaction in step 2. So we have H plus, and you're going to react that with the FeBr4 minus that you formed in step 1 when we generated the electrophile. And then what you can form is FeBr3 and also HBr. And so this here is a catalyst that we've regenerated. And also the reason why we call it a halogen carrier catalyst is because these catalysts contain a halogen. So now we're going to look at the combustion of benzene. So arenes burn with a smoky flame, and this is due to incomplete combustion. And so we form soot, which is carbon solid, instead of carbon dioxide when we burn things completely with enough oxygen. And this occurs as we have a really high carbon to hydrogen ratio. Arenes can also burn completely, but this is very unlikely because we have this high proportion of carbon in the molecules. And so that means that we would need a very high proportion of oxygen to the hydrocarbon to get complete combustion. And the general rule we have is that the higher the carbon to hydrogen ratio, the sootier the flame. And so now we're going to look at an example of balancing an equation. So we've got the incomplete combustion of methyl benzene. So methyl benzene is just benzene with a methyl group. So we have a methyl here, and then we're going to add on some oxygen, and what we're going to form is carbon solid and also some water. And this oxygen will be a gas, and this will probably be a liquid. And then what we do is we just balance it. So for the benzene, we have got 1, 2, 3, 4, 5, 6, and 7 carbons. So we need 7 here. And now for balancing the hydrogens, we need to remember that on this carbon here, we don't have a hydrogen anymore. We have a methyl instead. And so that means that the total number of hydrogens is 5 plus 3, so that's 8. So we need 4 of these waters. And now we balance the oxygens. So we've got 4 oxygens on the right, and that means we need 2 oxygens on the left.